People publish results that do not replicate because they thought a small p-value meant their claim was probably true. The misconception is treating the p-value as the probability that the hypothesis is correct or incorrect. Mathematically, the p-value is the probability under a specific null model of seeing data at least as extreme as what you observed, so misreading it flips the condition in the wrong direction. Picture yourself staring at a test output after a long experiment, seeing a small p-value and quietly letting that number carry the whole argument while the actual question it answers slips out of view. A p-value lives in a thought experiment. You imagine a world where the null hypothesis is exactly correct, including all its details about randomness, variance, and sampling. Then you ask how surprising your data would look in that world, measured against a statistic you chose before you looked. The p-value is that surprise, turned into a probability under the null model of seeing results this extreme or more so. The phrase this extreme or more so is not decoration. It encodes a rule about what counts as evidence against the null. You pick a direction or both directions of surprising behavior, you pick a statistic that compresses the data into a single score, and then you tally how much of the null world would produce scores at least that far out. That tail area is the p-value, and it is always conditional on the null being the generator of the data. Consider a website experiment that compares a new button color against the current version. And suppose you commit in advance to call it a win only if the p-value falls below 5%. That cutoff is not a magical truth detector. It is a convention that, under the null model, and with your test plan fixed, limits the long-run rate of false alarms to a small level. To picture what the p-value is measuring in that example, freeze the observed difference between the variants. Now spin up the null world in your head. In that world, there is no real difference between variants, so any gap you see comes from randomness in who visited and who clicked. Simulate that world by reshuffling the labels across visitors, or by sampling from a model that assumes no effect. Compute the test statistic for each pretend experiment, and watch where your real statistic sits relative to that reference distribution. The fraction of pretend experiments that look at least as extreme as yours is the p-value. Beginners often grab the p-value and translate it into a claim about the truth of the hypothesis. They say the hypothesis is probably right because the p-value is big, or probably wrong because the p-value is tiny. That is backward because the p-value conditions on the null being right and asks about the probability of the data, not the other way around. That mistake is costly. It creates false confidence in claims that just rode a lucky streak of noise. It leads teams to roll out changes that do nothing and to dismiss meaningful effects that happen to land in an unlucky sample. It corrodes judgment because the same number gets used to mean support for a claim, strength of an effect, and credibility of a study, even though it is none of those things. Here's the correction that stops that slide. Always read a p-value aloud with the null condition baked in. Say if the null were exactly true, data at least this extreme would show up this often, and then name what extreme means for your test. If that frequency is tiny, you have statistical evidence that clashes with the null model. That is evidence against the null, not proof of the alternative, and not a probability the claim is true. The cutoff you choose is a policy decision about how cautious you want to be with false alarms. It controls the behavior of your testing process across many uses, not the truth status of a single claim. If you treat the cutoff as an oracle for a particular study, you overfit your decision to a random draw. There's another quiet trap. Each test has a small chance of flagging a difference, even when nothing is there. If you try variant after variant, question after question, or slice the data many ways until something looks good, you turn that small chance into a near certainty. That is why a flexible analysis without a plan yields a steady flow of spurious discoveries. The p-value assumes you framed the question and the test before you peeked at the results. Related to that is the habit of peeking at the data and stopping as soon as a threshold is crossed. Stopping rules matter because the null world includes the path you took to look at the data. If you check results again and again and stop at the first lucky dip, the assumed null distribution no longer matches what you did, so the reported p-value is no longer telling the truth under the null. If you want to monitor as you go, use a procedure that adjusts for repeated looks or set aside a clean holdout at the end. Small p-values do not measure effect size. With a massive sample, a tiny effect can trigger a very small p-value because the test statistic gets sharp. With a tiny sample, a large effect can still produce a large p-value because the data are noisy and the distribution under the null is wide. Treat the p-value as a yes-no signal about incompatibility with the null under your plan, and use separate tools to measure how big the effect is and whether it matters. When you read a p-value of 3%, read it as follows. If the null model were the data generator, results at least this extreme would show up about that often across many repetitions of the same design. You can say the data are in tension with the null by that standard, but you cannot say your favorite hypothesis is probably true. When you read a p-value of 40%, do not say the null is probably true, say the data are not unusual under the null. So this test did not produce evidence against it. The mental shift is from treating the p-value as a verdict about truth to treating it as a calibration of surprise under a clearly defined null world. That means naming the null model, naming the statistic, naming what counts as extreme and in which direction, and respecting the analysis plan that gives the reference distribution its meaning. Once that discipline is in place, the p-value becomes a precise tool rather than a vague badge of credibility. Next comes confidence intervals, what that plus or minus number really means, because after you know how to read surprise under null, you need a clear way to state plausible sizes for the effect you care about.